So in corrosion, all these things are on the website, okay? Now, there was a guy in Europe after World War II in Belgium. His name was Marcel Courbet, and of course they had no money, they barely could eat in Europe after World War II. And the Navy started the U.S. Office of Naval Research and actually started funding some work. We brought back a lot of the scientists to the United States, like Werner von Braun, you know, the rocket scientist for the Germans, and this guy Ragnar Holm was electrical contacts expert. We brought back hundreds of top-notch scientists from Germany. But not everyone came back, and they had no money to do research, they had no laboratories. The U.S. Navy started the Office of Naval Research in London, and the Navy, U.S. Navy used to fund projects in Europe with some of these top-notch guys who were still living there, who didn't want to come back. Marcel Courbet, instead of being an experimentalist, he decided to calculate the thermodynamics of corrosion. Okay? Actually, he called it Atlas of Electrochemical Equilibria in Aqueous Solutions. Aqueous means water, guys. Okay, I do that. Okay, electrochemical equilibria. Corrosion is an electrochemical process. Corrosion is a chemical process. Most corrosion, there's also hot corrosion, which is not electrochemical, but in aqueous solution, you got a bunch of little ions. And most metals want to go back to their native state. The only metal that is not an oxide or a sulfide in nature is gold. Okay? You find metallic gold. You can find metallic copper, but it's just in the process of corroding slowly. So Courbet came up with, and he did this for a number of years, but he came up with a technique to be able to calculate diagrams, now called Courbet diagrams. And the Courbet diagrams, you know, here's a Courbet diagram for boron, and here are some of the equations. You don't have to worry about it, but here's the thermodynamic data, which was available in the literature, and he ended up coming up with a way to calculate a diagram like this, and you're plotting two things here. Two things. You're plotting the pH of the water. 7 is neutral pH, 0 is really acidic, and you can go -2. This is a log scale, okay, of a pH scale. You go out here to 16. 14 is considered as basic as water gets, and this is acidic. So this is acidic to base, neutral is 7, the way they define it, versus the electrical potential in volts. Okay? And this goes up to 1.8 volts, this goes down to -2 volts. The stability of water is between these two lines. When you were in high school, you took water, put an electric current through it, and you made oxygen at one electrode, and you made hydrogen at the other electrode. Hydrogen was at the cathode, and oxygen was at the anode. So this is anodic up here, where things tend to corrode, and down here is cathodic, where things tend to not corrode. So the potential, now, you can calculate things that aren't even as stable in water, because you're just doing a calculation, and you know, actually he didn't even have a computer, he was doing all this by hand. So it turns out every metal wants to go back to its natural state, and you can take some of these. He has it in the beginning of that book. He tells you how to apply this to corrosion problems. He tells you how to apply it to a bunch of other types of problems. But we have lots of places where we deal with the reactivity of something in a wet environment. And corrosion is in a wet environment most of the time, except hot corrosion. And he did do a bunch of diagrams for hot corrosion that I didn't bring in. We don't have so much time. But you can do this for everything. He's done it for basically every element of the periodic table. Here's zirconium. Remember, these two black lines are the stability of water. Pure oxygen up here, pure hydrogen down here. Water exists stable right here. Zirconium. Okay, this is, I can't read column very well. There's corrosion by dissolution, corrosion by gasification, passivation by oxide or hydroxide layer. Zirconium is completely passive, which means it's got an oxide scale that protects it from corrosion in water. Oh, between pHs of about 5 and 10. Aluminum is not quite as good as zirconium. Hafnium is even better, except it poisons your reaction. Beryllium, titanium. Titanium, look at titanium. You can't corrode anything in water in titanium. Titanium is almost completely impervious to corrosion in an aqueous environment. That's why we make medical implants out of it. That's an aqueous environment. Now, if you start adding other things like chloride ions, sometimes you shrink these things down by quite a bit. In fact, this may be, well, here's the chromium down here. This is why stainless steel is corrosion resistant. Chromium oxide, over a very wide range, from very basic, like pH of 12, over to pH of 4 or 5, chromium oxide doesn't get attacked. Very acidic things will eat up stainless steel.
So this is all theoretical, that like it's a perfect, alloys.
This is without alloying. You can do it with alloying, and they have done it with alloying. This is just take an element and say how corrosion is resistant is in thermodynamic terms. Is it energetically favorable? And this is basically putting the oxide on the surface. And it tells you the range where you could get corrosion, which is this region up in here, but not down in here. But, okay, that can change under certain conditions, and then you have to understand what those conditions are. That's the thermodynamics of corrosion. So by 1950, we knew the thermodynamics of corrosion. What we don't know, and we can't predict with any regularity, and people have tried, is the kinetics, how fast something corrodes. Most times, here's vanadium, well, vanadium, zinc. Okay, zinc is actually can form a protective layer, but most cases, in most water environments, zinc will slowly corrode. That's what you use the zincs for. You're using them to corrode. But how fast does it corrode? Why does galvanized steel last so much longer than regular steel? The zinc corrodes kinetically at about 1/5 to 1/10 the rate of just straight iron. These diagrams are thermodynamics. They're not kinetics. Okay, kinetics is time dependent. Thermodynamics is stability. If it's stable for eternities, right? In theory, unless it can be metastable. Okay, but we have an atlas that tells you everything you need to know about thermodynamics. It tells you nothing about the kinetics. And the kinetics is still kind of experiential. Okay, although we have data on it. I mean, my rule of thumb is carbon steel corrodes at about 4,000ths of an inch per year in the atmosphere. Rain, in New England, okay? You just put a piece of steel out there, you come back a year later, you'll have 4,000ths, you'll lost 4,000ths the thickness in rust. And so someone come to me and say, okay, we have this 1/4 inch steel pipe and it corroded in 1 year. I say, no. 4 into 250 is about 60 years, okay? And if I put chlorides in there, maybe I can speed it up by a factor of 2 or 2.5, but it still took a decade. I mean, a 1/4 inch steel pipe is going to take a decade, okay? And if you start thinking about your seawater piping on some of your older ships where they use carbon steel, you can project why you have 30 years life with the type of wall thickness you have. That's the corrosion rate of iron without any protection. Okay, so we know empirically, people have done lots of measurements on how fast something corrodes in a given environment, and there's lots of databases that will tell you about those things. But in what's his name's in Courbet's book, he has a chart, which you will have in your stellar stuff, that he talks about thermodynamic nobilities of the metals and practical nobility. Thermodynamic is it immune? Which is the most immune metal? Well, the most immune metal is gold thermodynamically, and the least is magnesium. I told you, we don't use magnesium for structural things because it corrodes. In fact, it's not just bad, it's the worst. Okay? Take virtually anything you want on the periodic table, and magnesium is worse. Okay? From a thermodynamic standpoint. Number 2 is iridium, okay? Number 3 is platinum. Is that platinum? Okay. Turns out, that's why when I made my wife's engagement ring, I electron beam melted out of platinum iridium alloy. Couldn't buy it at the time, but I knew it was corrosion resistant, immune from corrosion. Anyway,
True story?
true story, but there's more to that story about how I was working on an electron beam melter that actually was one of the last time someone got killed in the laboratory on Christmas Eve of 1962. Gunter Conradi they used to have sparks, and you hear this zap, and they knew it was this one wire. He reached down, it had been raining that night, Christmas Eve, and his soles of his feet were wet. He reached down to pull the wire away so it wouldn't be sparking, and he electrocuted himself. 6,000 volts will do that to you.
You were right, like next to him in the same lab or something?
No,
or
no,
what?
62, I was in elementary school.
Okay.
But in 73, I was using the same piece of equipment which they built all kinds of Faraday cages around to make it. But I'd be sitting there, I built a little rotating cable that I get inside the vacuum system, and I was rotating it and melting the little ring of platinum iridium, and I'd hear zap! And of course, there's all in Faraday cages. This went on for about 3 weeks while I was doing this time. Here's this zap. And finally, Technician Pucker and I said, we got to fix this. And I didn't tell my wife this story for probably 30 years. But so I heard zap, zap. And we finally found inside a, what do you call these things? The Army uses. In fact, this was an Army old radar power supply that we were using from the Korean War. And they have these screw-on connectors. I mean, they're this big around. Cannon plugs, cannon connectors. There was a cannon connector, and inside there were the 2 leads, and then inside a big insulated area, and the 2 leads, there was carbon arc tracking in between there. It was zapping inside a cannon plug. So I was completely safe, we just didn't know that. But I didn't know, I knew that Gunter Conradi had killed himself like this. I never told my wife until a few years ago. Anyway, so, you know, you got a whole bunch of things, mercuries, you can go through the list if you're really interested. But the best in practical ability in terms of passivation meaning you form a protective oxide on the surface, is rhodium, better than gold. And niobium and tantalum, which are way down here, look at some of these guys. They form such stable oxides. Tantalum capacitors are the best capacitors for long-term stability. We use them in computers as storage devices to store some data sometimes. But tantalum capacitors form a tantalum oxide film. Extremely stable, even at very high voltages, okay? If we go back to the Courbet diagram, you can decompose virtually any metal with 2 or 3 volts in water. I was working with Johnson & Johnson back in the 80s, and they use electrocautery to basically cauterize a wound. They just go in there with a couple of electrodes at 100 volts, pass a little current through your skin, and it basically dries up the blood and the proteins, you know. And so it can cauterize. You got a leaky vein or something messing up the surgeon. He's got blood all over where he's, so he wants to stop the bleeding. He can go in there with these 2 little probes, put 100 volts there, and essentially clot the blood right there locally. But the problem is, one of them's positive, one of them's negative, and the anode, which is positive, was always corroding. 100 volts will corrode any metal. And they were using stainless steel, they tried nickel alloys, they tried all the corrosion resistant metal. They came to me and said, Tom, what are we going to use? I said, nothing. Okay, because if it's a metal, 2 volts will corrode any metal.
Even gold.
Even gold, even platinum, you name it. Because the thermodynamic immunity, you can get the stability of the oxide or anything else. I said, well, yeah, you could use gold, but even gold will dissolve in a chloride-based solution. Gold oxide won't form. But what's aquaresia? Aquaresia is just an oxidizing chloride solution. You take hydrochloric acid, you take nitric acid, mix them together, and it will dissolve gold. So if you take the chlorine out of the person, you could use it, but then they'd be dead. Okay, because you're made out of salt water, you know. Okay. So there was no solution. I said, make the tips so they're cheap and you can sell them in one for every operation. Just make a disposable tip, right? They're gonna corrode, so what? A little iron won't hurt you. It's good for the blood. Anyway, so they have these different things, and you can see they change places, and some of these things, hafnium, beryllium, very reactive metals, aluminum. And they get their corrosion resistance from a very stable surface oxide. Okay, there are a few little principles. Well, actually, I can talk about the forms of corrosion first, maybe. There's a book, actually I used to hand out a whole chapter out of a book by Fontana and Green called Corrosion, a catchy title. I'm sure they need a lot of people for that. And he talked, their outline of this 400-page book, which is sort of in its third edition and classic, comes out of Ohio State, which has a big corrosion center and has for 60 years. Their index has the 8 forms of corrosion. And then the National Association of Corrosion Engineers came out with this pamphlet, Forms of Corrosion Recognition and Prevention by C.P. Dillon. He's a big corrosion stainless steels expert. Pretty old now. But in here, he talks about the 8 forms of corrosion. The 8 forms are uniform general attack is one. So the surface just eats away. We know that as in steels as rust. Okay. You have localized attack, which is localized corrosion or pitting, or crevice corrosion is localized because you get a different oxygen potential inside the crevice or in the pit. For some reason, that surface oxide breaks down. Chlorides will break down the surface oxides in a lot of things. So stainless steels pit in seawater terribly, but they don't rust, okay, generally in seawater, okay. You get into other things, they call this, he calls it velocity phenomena, erosion. Well, that's when you lose the copper oxide on the surface. We talked about that, okay. Cavitation, big problem in propellers. You have a certain velocities, particularly on a propeller. One side you're creating suction, and the other side you're creating positive pressure. They have to kind of balance across that propeller to a certain extent. But on the suction side, you may get to the point where the water vaporizes, and you get little bubbles. And those bubbles, when they collapse, reach a singularity, just like that wave of water forming the, the copper thing in the thing, everything coming to the center to a singularity point. You can get 10,000, 20,000 PSI pressures when that bubble collapses. So you ever seen an ultrasonic cleaner, a water bath, and you throw rings in or something like that and it cleans? You're creating cavitation. Even whether you can see the bubbles or not, you're getting microscopic bubbles which are pounding the surface with 10,000 to 20,000 PSI pressures. And that can just mechanically beat away this protective surface oxide and give you corrosion. Not only is it a problem for sonar, it's also a problem for corrosion of propeller blades. Okay? Or other things. Fretting, microscopic wear can wear away some of the oxides and cause some corrosion. It's fretting down here. That's application up there. Intergranular attack, we talked about that in stainless steels. Weld decay, that's the same thing as the stainless steel stuff we talked about. There are other things like exfoliation, where you actually corrode between the pancake layers. This occurs in aluminum alloys, but we know how to control it with the proper heat treatments and alloys. Now, I've only seen 2 cases of exfoliation corrosion in my life. One of them was in a 1948 seaplane being operated about 4 or 5 years ago in Miami, crashed in Miami Harbor. It's in the news a lot. But it's just old alloy, if you will, in the 1950s. Okay. The other one I saw was some guy decided to build his own, what do you call the water power where you just shoot out a jet of water for your motorboat? That's a drive rather than propellers.
Jet propulsion.
Jet powered water jet. It's a water jet, basically. You don't have a propeller, you're just pumping water out the back end. So this guy up in Maine decided to build his own fishing boat with a water jet pump. And he had decided to make it out of aluminum, and he used aluminum alloy, and it had enough velocity, okay, coming through that water going past there. It's just seawater that he ended up with exfoliation corrosion. wiped out his tubes within 6 months. Okay. So changing velocities and things like that, you can set up different potentials, and it was exfoliation corrosion. There were alloys he could have used that wouldn't have had that problem, and I think that's what I ended up recommending. De-alloying attack happens in copper zinc alloys, for example, copper aluminum alloys. It can happen in a few other alloys, where one very reactive metal, in this case zinc and brass alloys, can be leached out and leave behind an almost pure copper residue that's very porous and very brittle, and can cause failures. Very slow process. The only real failure I've seen from this was a 30-year-old plumbing valve down here in Dedham, Massachusetts, and it had been de-zinkified over 30 years, and it just lost enough strength that it just broke off. Caused a flood in the home, cost $500,000 damage because it destroyed 2 original John Single copy watercolors that were worth $400,000 of them, $500,000. Stress corrosion cracking, we talked about that with stainless steels. Occurs in a lot of alloys, but usually in alloys that are almost immune to corrosion. Corrosion fatigue is basically the same thing when you have dynamic stresses and you get a fatigue crack, they can grow much faster. Okay? Once I had a problem with a helicopter rotor blade down in Brazil. These guys had decided that Bell Helicopter was charging too much money to do the work on the rotor blades. The rotor blades are sort of a critical element, and Bell recommended you send it back to a Bell authorized service center. Okay, but they're pricey. So these guys decided to do their own repair. They took off the corrosive preventive paint, had a ding in the blade, and they just kind of blended it smooth, got rid of any stress concentrations, and then they didn't do a very good job painting it again. Okay, and it turns out they went to fly it, and within a couple of weeks, the blade flew off, killed a few people, and everybody said, "Oh, you got." What was their argument? Their argument. I can't remember what their argument was, but the Brazilian transportation authorities and the U.S. authorities and Bell all determined, oh yeah, we got a problem with the design or something. And they issued an alert service bulletin and stuff. And I came in and I looked at it, I did some fracture mechanics, I said, no, you could never grow a fatigue crack, get corrosion fatigue there, unless it was stress assisted. It was corrosion assisted. It was stress corrosion cracking, or stress corrosion fatigue. Because if you looked at the final size, the stress in the rotor blades they got like a factor of 10 safety of stress. Okay? And the final ligament that failed was not very big, and so you knew how much stress was in it. And you look at the size of the original flaw that everybody was pointing to. Oh, they thought it was corrosion pitting. It was pitted, and this fatigue crack grew from the pit. I said, no. Okay? It grew from the pit, if you did the fracture mechanics, because of corrosion fatigue, increasing the fatigue rate, not because of just pitting corrosion. Everybody said, oh, it's pitting corrosion. And so they were increasing their specs to look for finer and finer pits. And no, you have to not let people put it back in service without paint on it, okay? Okay, you gotta protect it from corrosion. So anyway, corrosion fatigue, you get an interaction between the stresses and the corrosion, and you get things, cracks going pretty fast. Scaling is high temperature attack, internal attack. We need to talk about that. There have been some big failures on some of those things, but we don't have to worry about it. The scales that form, such as rust, can actually be very protective. So this is out of a marine handbook, marine corrosion handbook. And corrosion prediction, rate prediction of ship steel and seawater with and without flexing. Okay, this is the attached rust, with attached rust, and you get clean steel, starts rusting very quickly, but after 100 days or so, the rust basically starts becoming just as protective as paint, okay, or almost as protective. Up here in the shear straits, I guess, you get very high corrosion because it's flexing up there and you're breaking off the brittle rust. One of the things about paint is it's got to be flexible enough to adhere even though you're stretching the metal a little bit, okay? So this is, you had the same high corrosion rate locally, you can see the spikes in here, but you have to ask yourself if removing rust is good or bad. In fact, when they were redoing the subway station down here at Mass General, right across the river, the guys who were doing it was a firm I used to consult with, Civil Engineers, SPH, which was a spin-off of MIT Civil Engineering back 60 years ago. And they called me up and said, this was 1910, they built this subway station, old riveted steel and stuff. And they had areas of rust that were half an inch thick. And they were replacing some of the beams. And in some cases, they had concrete, and they go in there and they chip out all the rust down to white metal. And they called me up and said, Tom, now what do we do that got down to white metal? I said, you better plug it up with something, because that rust was protecting it from corrosion. You just remove what has kept it from corroding for the last 80 years of the 100 years it had been in service. So you have to grout it up to keep it from corroding.
So sir, yesterday or before the presentation, you mentioned that although the corrosion provides some protection, you said it also causes hydrogen improvement.
Yeah, when you corrode, you're basically breaking the water down into hydrogen and oxygen. Some of that hydrogen can get into the steel and cause hydrogen embrittlement. I've had a couple of things where people use high-strength bolts at some pier in New Jersey or Connecticut. Okay, I've had them in both states. And they figure, oh, we'll use 140 KSI bolts, okay, the different grades of bolts. And they put them in there, and they don't do anything to give them cathodic protection or anything, just put them in there. And they might have zincs, but the zinc stuff don't always cover as well as you might like. And within a year or two, these things are breaking intergranular failure, hydrogen embrittlement. And it's basically the bolts didn't have hydrogen in them when they started. And hydrogen embrittlement usually occurs in a couple of weeks if it was in there to begin with. But as it corrodes, the hydrogen gets in there, maybe in small amounts, but it still helps that crack grow. And we actually call it static fatigue. We do static fatigue tests in welding. You basically just take a threaded rod, like a bolt, and you weld over the end of the bolt. So you have a natural notch, no matter how deep your weld metal goes, you actually have a notch right there at the fusion line, right? Because it's a threaded notch, okay? And you just put a load on it, just a static load, 60–70% of the strength of the bolt, the threaded core of the bolt. And you wait and see if it'll last 72 days or 72 hours or not. If it cracks with it, you plot the number of hours to see how severely embrittlement it is, okay, by your welding process. Okay, so called the implant test, because you implant a steel bolt in a hole in a steel plate. You weld over the plate and the tip of the bolt. You're implanting the bolt into the steel. It was developed by a French welding engineer 50 years ago. Okay. Simple test. Simple test for regular bolts that come out of heat treatment where they may add zinc. You basically have a plate. You tighten them down to the proper torque. On a plate with a bunch of threaded holes, you put 8 or 12 of them in there at the proper torque. You come back 3 days later and see how many of them cracked from hydrogen embrittlement from the electroplating operation. Okay, the electroplating operation will introduce hydrogen. Okay, because you're laying down positive zinc, positive cadmium, whatever you're plating it with. Well, positive hydrogen goes with it, right into the steel. I mean, this is not, big new science to know that positive ions all go to one location and negative ones go the other way. Hydrogen is positive ions. So if you're going to do electroplating, you're going to have to bake out your steel. Okay, I had a case. It was called a pea shooter. It's basically a spline tube, and it goes from the engine to the transmission of a helicopter. Okay, just like a 3/4 inch diameter high-strength steel tube. And to prevent the wear of the splines, because you're just inserting the spline male into the spline female. And the spline female, when they made it, they wanted to nitride the surface of the steel to make it very hard, very fretting, corrosion resistant, and things like that. And they had a spec that after they took it out of the heat treatment situation, the nitriding bath, they had to bake it for 1 to 4 hours, or for 4 hours to get rid of any hydrogen that might be there. But they decided they needed to know, at this aircraft manufacturer, whether they had the proper thickness of the nitride in the case. So they would go through the whole process, they'd cut a piece off one of their exemplars, they destroyed one part, cut it, send it back to the Met lab, and 3 days later, they would get the part back to tell them if they'd done enough nitriding, and if they had, they would then do their hydrogen evolution heat treatment. Well, that's sort of like preheating the Friday before, right? And when I saw this, and it turns out it was, I think it was a Canadian thing or something, and the Canadian ex-metallurgists could not see this because the aerospace company basically said the ATARs, trafficking in arms, you Canadians, just like the Soviets, we gotta be careful about it. And so they hired me because I was a U.S. citizen and I could read these confidential documents because I was a U.S. citizen. But the Canadian metallurgists couldn't, okay, because it wasn't U.S. citizen. Sort of, I got paid for it. But anyway, I read the process spec, and they had this 3-day delay, and this is one where I had to call up the attorneys and say, look, you better tell the attorneys for this aerospace company, they got a problem that could kill some more people. Because this is why they were getting embrittlement and cracking in their pea shooters and losing power to their transmission in their helicopters. And because my duty as a professional engineer is to my first primary duty is to the public safety. People could die. Even though I was involved in some sort of lawsuit between the helicopter company that lost a couple of employees and the aerospace company that had made this engine, I couldn't wait until 3 years when they finally solved the problem. But I couldn't just go and tell the attorneys on the other side, the aerospace, I can't contact them, I'm sort of barred from doing that. So I told the attorneys, I said, this is serious, you have to tell them. And you got to get back to me and let me know when you've told them that they have a serious problem. And they told them, and the attorneys on the other side, they just laughed, oh, Professor Avery, I know what he's talking about. Okay, hey, I've done all I could at that point, right? But sometimes they're sort of in a, and I've had that type of situation 2 or 3 times in my career where you can't just wait until everything's over to tell people they have a hazardous situation. You have to do it. There are some things that you ought to know about seawater corrosion. First of all, this is the corrosion rate of AISI 1010 steel or other steels as a function of oxygen, or corrosion rate in meters per year. Must be millimeters per year. Anyway, it might be a typo.
Meters.
Oh no, that's depth. Whatever. Anyway, no, this is depth. This is depth of the ocean. And at the surface, you have a lot more oxygen present. And your corrosion rate, basically, of your steel follows the amount of oxygen in the water. Duh. Okay? As I always say, the reason we have iron piping in our boilers in our homes is because you shouldn't be getting any oxygen in there. It's a closed system. Once you consume the oxygen that's there, there's no makeup water to bring in new oxygen. But our potable water piping is full of oxygen, and there's corrosion, so we have to use copper with better corrosion resistance and higher cost, or plastic nowadays. Nothing problems with plastic myself in many cases. I always say if the fish can't breathe, okay, the water is probably safe against corrosion. But if the fish can breathe, you got to do something so you can kill all the fish in your bottle of water or whatever in your boiler. One time I got about a 2-inch diameter pipe, or maybe 1.5 inch, completely occluded by rust. And this has been in a big warehouse. I don't know how big. They told me that all the pipes, this was a huge warehouse, everything was occluded. They were going to have to replace all the steel piping in their fire protection system. And I looked at it, and they wanted me to do some tests and tell them why. And I called them up, and I couldn't do any tests. I said, "You guys have a leak in your system." "Oh yeah, we know." they had a leak, and it was kind of a stream of water that they had just go running into a drain. They had that for a couple of years, okay? And they didn't fix it. And I said, well, you're gonna have to replace all your piping because it just corroded, because that stream of water and the makeup water was bringing new oxygen to the system, and it's corroding it. If you were supposed to have a closed system that didn't have a lot of makeup water. You can tolerate a little makeup water, because you only have a little bit of oxygen. But you don't just let the leak go. They just didn't bother to fix this thing. They knew they had a leak. I said, well, too bad. You gotta replace all the pipes. They're all full of iron oxide. So that's why you bring a reactor in to port, and you shut it down, and you make sure you get rid of the oxygen. Startup of commercial reactors, they basically boil the water in a separate system before they turn the reactor on to get the oxygen out. Okay, they actually do vacuum treatment. I don't know if the Navy does that. Jack, they probably do something. They do something other than hydrogen. They do belts and suspenders in the Navy.
Vacuum treating of what?
The water, just to suck the oxygen out.
Oh, sure,
Deaer-
yeah.
deaer-
Okay, the plant.
Yeah, the whole plant can be
Yeah,
deaerated.
never cared about that.
So, I mean, I don't know or care how you do it exactly, but the Navy will store it under hydrazine, and they
Right.
deaerate before startup by something. And they do that for commercial reactors. This is an example of hot corrosion. At high temperatures, not aqueous systems. This is what a turbine blade was supposed to look like. This came out of a commercial airliner engine. Actually, that one came out, but this one also came out of a commercial engine that was operating. Okay, sort of deformed. This is hot corrosion by sulfur. Oxygen and sulfur are the two things that create problems. And here's actually the plot, and you have to notice there's a break here. So this is 20, and this is 200 up here. There's a break from 100 to 180. This is the corrosion rate. It goes up by a factor of 100 in a very narrow temperature range. So you usually are doing your work, well, up here, it's too hot for the sulfur oxides to condense on the surface. If you look at where it's corroded, there's all kinds of bubbles. Those are sulfide bubbles, or nickel sulfide bubbles. Over here, the kinetics are too slow for the fusion to occur. But in a very narrow range of 100 degrees centigrade or so, you have a local increase in corrosion rate. Now, what we usually do with startup is you start up the engine, you don't power it up right away, you let it warm up for a couple of minutes before you go take off. This actually happened to be a Mexican airline. Fuel was high. We think that they were basically, to save energy, they were basically starting their engines and then going full power takeoff without warming up their engines properly. Instead of takeoff power, getting them in this range where you don't have corrosion, we think takeoff was, they were getting a couple of minutes in this range because they hadn't preheated their engines by letting it just warm up to closer to equilibrium temperature. So little changes sometimes make big differences. This is my one-page principles of corrosion. Everything you needed to know about corrosion as a manager. Most metals except gold want to exist as oxides or sulfides. We covered that. Metals may possess inherent nobility, or that's immunity, or protective oxide scales. Almost all the metals we're dealing with have protective oxide scales. And anything that destroys that is you're going to get pitting, general corrosion, stress corrosion, cracking, whatever. It's those protective scales that are making things corrosion resistant. Chrome oxides, aluminum oxides, the reason we use them, I told you manganese, aluminum, bronze for propellers is because the aluminum gives a very protective oxide. Free oxygen sulfur is required for corrosion. If the fish can't breathe, it won't corrode. Moisture provides the electrical pathway for chemical charge transfer. We store aircraft, aged aircraft, or we put in the desert outside of Tucson because it's dry. It doesn't rain very often. Moisture causes corrosion, so you can't store all these. You have to have acres and acres of hangars to store all these old aircraft, B-52s or 747s or whatever. We just store them in the desert. Corrosion occurs less in the desert than it does in the New England. Stratofortress, yeah. I mean, there are pictures of where they have to take the wings off so we can take pictures from their satellites to see that we've destroyed the aircraft, like, you know.
Did you hear about the refurbished, I think, Stratofortress that they're either doing or just finished?
No,
Yeah, they just did one version.
just for.
Oh, just restored one.
So moisture is a problem. You guys, you're stuck with moisture. I mean, it's there in the Navy. In fact, if you didn't have it, you wouldn't have a Navy. So here, localized corrosion is due to electrical differences like crevice corrosion or exfoliation or pitting when you have little copper areas and aluminum alloys, and you get cathodes and anodes. Okay. Velocity phenomena is due to mechanically breaking up that oxide scale. De-alloying is selective leaching. We don't have to worry about it too much. Stress corrosion cracking we talked about, and hydrogen. Boy, you ought to know that by now. Okay. So that's it. 3 minutes spare. Ask all the questions you want.
See, I wish I'd known
Hey,
some of
Steve,
this
that
when
one up.
the XO walking around, you know, pointing at rust. I could have been like, sir, I'm just trying to protect the metal.
Professor, you put that one back up, the last one.
The last, sure.
I mean, if the Navy accepts that, that'll be good for a lot of boatswains out there.
It's aluminum is good to go. Aluminum
They
has
serve
coating
right
like this.
themselves that are-
This one, yes.
Saw that.
What one?
Yes, that.
Hmm?
Oh, it's yeah.
Oh, it's on the, it's on the
It's one of
internet.
the handouts.
It's on Stellar.
Okay. Take the time.
No, I mean, if it's not on Stellar, tell Shaq and I'll have Jerry send you a copy. But I know all this stuff is on Stellar.
Good.
Oh, the one last thing I ought to tell you, I mentioned this to you. Before you, a lot of times, with the students who do the presentations all at the end, it's not like the summer schedule. I often hand out this paper by Tufte, who was a professor at Yale, who has made millions of dollars by teaching people how to communicate better. He despises PowerPoint, okay? And so he wrote this paper on, and this should be on your Stellar site. But he had PowerPoint, what do they call it, some auto formatting. You put in some prose and it will make up your own PowerPoint slides based on its sort of artificial intelligence way. And he would say it's artificial intelligence, which means, but it is, okay. This is the Gettysburg Address in 6 PowerPoints. Okay, so here's the PowerPoint of the Gettysburg Address. Okay, got the title, the author, organizational overview. Minus 87 years.
Yeah,
Agenda, met on the battlefield, that's good. Dedication of portion, fitting. Unfinished work, great task. Okay. Review of key objectives, critical success factors, not on the agenda. And summary, new nation, civil war, dedicate field, dedicated to, new birth of freedom. Okay. This is what PowerPoint can do for great literature. Okay. And so think about it. We can have a class, and I'm not trying to make you guys feel bad, but you need a little help on your PowerPoints, okay? The best speaker uses no overheads, okay? Just keeps you interested in what they're saying. PowerPoint is a crutch where we just read back what's already on our slides because we haven't really got a lot to say, okay? Some of you use things that are a little too small to read. I've done that, I just did that a couple of times here. But you know, in a PowerPoint, a good presentation, if it's too small to read, why are you even showing it? Okay? Some people put something up for 2 seconds and, you know, well, why bother to show it? I would say 50% of your slides you really didn't need to show, okay, in many cases. It's the old story of, I can't remember who said it, but the person was asked if they would give a 2-hour talk on such and such. He said, well, if you want a 2-hour talk, I'm prepared right now. If you want a 15-minute talk, I got it. Okay? It's a lot harder to prepare a short presentation than it is to do a long presentation. Okay, anybody can fill up time. So anyway, but I brought it up now rather than when an individual will say it, because it might take offense. I'm trying to be offensive. I actually often am offensive, but I'm not trying to be.